Well, being the last talk of the summer school, I think it's due for us to thank Philippe for organizing it, and as well Fanny for assisting us, and all the other helpful assistance we got from everybody that's unfortunately not here right now, but that's something. That's the spirit.
Thank you for all the stuff.
Yes. Yeah, I will give my presentation will be a little bit more quickly, maybe, and going through a couple more problems than Philippe. But so let me start with what's already known. We didn't tell you yet everything that's known, but I can pretty much sum it up fairly quickly. So in some sense, I see there are 4 directions in which you can generalize problems in this area. So I will just quickly write them down, and then I'll go through them one by one to tell you what's done already, and then afterwards I'll tell you some open questions. So so the first direction is codimension. The second dimension is what kind of ring you're using. The third dimension is what kind of subgroup you're using. And the third dimension is what kind of algebraic group you're using. Okay, so let's go through these one by one. Codimension. So codimension, we already told you the most about. So let me just quickly repeat. There is the Church-Farb-Putman conjecture that says H, VCD, and I'm just going to write VCD in this talk because there's going to be a bunch of different VCDs. Minus I of SLN Z with coefficients in Q is 0 for n greater or equal to I plus 2. And what we know already, we know this, for I equals 0. This was the result by Lee Sharber in the 70s. Then we know Jenny presented that. Then we know this for I equals 1 for codimension 1. This is the result of Church and Putman that I presented yesterday. And then we also know this now very recently. So this is a result from 2015 or so. And this is very recently, we just posted this on the archive by Benjamin Brück, Jeremy Miller, myself, Robin Sroka, and Jennifer Wilson. So this is it for the Church-Farb-Putman conjecture. And as I said before, if you can, or maybe I haven't said that, but if you can prove I small codimension 3 and 4 as well, you can try to give Philippe a run for his money and scoop in on K12 of Z being 0. So that should be the goal of any confident mathematician, right? Okay. But then you won't be invited to France and fancy dinners anymore. So that's maybe one should rethink one's life choices. Anyhow, there is also the we've already talked about this a bunch in different lectures. You can choose all kinds of rings. Actually, maybe I should mention this. This is I don't think I have this on here in my notes, but I want to mention this. Actually, and not quite the Church-Farb-Putman conjecture, but something very similar is known already for fields. So let me write this This is a result by Ash, Putman, and Sam, by Avner Ash, Andy Putman, and Stephen Sam. They prove that H lower I of SLNF for any field with coefficients in the Steinberg module of that field, that this vanishes for n at least 2i plus 2. So this is quite similar to this result here. You want to prove the same thing for SLNZ. The range is a little worse, but I think the range was improved by Søren Galasios, Sander Coopers, and Oscar Linder Williams. So, and they actually proved this not only for SLN, but also for all reductive algebraic groups, which I get to those things a little bit later. But actually what I meant by rings here is to say what happens to other number rings other than Z. That's basically the question here. And so one thing that is also known is that, I mean, and Jenny presented that, this is the result by Lee Schaber, in fact, prove that H naught of any SL, any ring, so R is Euclidean, might be norm-Euclidean now that I'm thinking about it, but let's, let me put this here in parentheses. I have to look this up. SLN R with, if you, well, let's just say Q tensor Steinberg n of the fraction field of R, that this is 0 for n greater or equal to. So this is true for all Euclidean domains. Norm Euclidean domains. So in particular, this is true for number rings that are Euclidean domains. And so for number rings, if R is a number ring, then this is the same as saying that it is 0 in the BCD, right? That's the same thing. Now let's stay in codimension 0 for now and say what's going on there. Now, not all number rings are Euclidean, but all number rings are Dedekind domains. And so all number rings have a class group. And Church, Farb, and Putman, Tom Church, Benson Farb, and Andy Putman proved that if, so OK is a number ring, then the dimension of the top cohomology of SL and OK with coefficients in Steinberg of K, K is the number field, is greater or equal to the size of the class group. So this is a finite number, and if you have a PID, that number is 1. You just have you only have principal ideals, but in general, if you don't have a PID, this is bigger than 1. This is always larger than the class size of the class group -1 to the n minus 1. So in particular, this shows that if OK is not a PID, then BCD is non-zero. I'm so sorry. I shouldn't. I hope you were all confused. You were expecting to see trivial coefficients here, because then you can take Borel-Serre duality to say homology and Steinberg coefficients. That's what I actually meant here. But sorry, so this is not equal to 0 then. So you have top cohomology for Euclidean number rings is 0. You have for number rings that are not PIDs, it is not 0. So what about PIDs that are not Euclidean? That's kind of left here, right? So I guess we don't know exactly what all the PIDs are that are not Euclidean, but assuming the generalized Riemann hypothesis, generalized Riemann hypothesis, gotta be frank with you, I don't know what this exactly says, but I'm sure maybe you guys know better because you have maybe closer relations to number theory than I do. But I know, or I don't know why, but I know that this implies that the only number rings that are PID but not norm Euclidean are come from, so are OK for K equals Q of this quadratic extension for D equals -19, -43, -67, and -163 are the only number rings that are not PID, sorry, that are PID, but not norm Euclidean, but not norm Euclidean. So that's a finite number of rings to check. And here, in fact, I can shamelessly plug another theorem of myself with Sandra Coopers, Jeremy Miller, and Jennifer Wilson. We proved that HVCD of SLN OK rational coefficients is equal to, sorry, I have to be precise, 2n, and we can only prove this for even numbers, even rings, is equal to 1. Oh, sorry. Let me say the dimension is greater equal to 1 for D equals -35, 2 to the n if D is equal to -67, and 6 to the n if D is equal to -36. 163. Mind you, the case for -19 is still open, but note that the BCD of SL2 OK for D equals -19. So in degree 2, this is 0. So that's different here, right? You see, if you plug in n equals 1, it's 1-dimensional, 2-dimensional, 6-dimensional, and this is really what we elevate to all n. Then that's what we use in this paper, but we can't do that for 19 because it's 0 in degree 2. So what's just codimension 0 for all these number rings? What's still open? Whether it's 0 or not, the only things that are open are is basically all of negative 19 here, and then all the odd degrees of these 3 numbers. Everything else is known. Yeah, for codimension 0. Questions? Feel free to ask a question if you want to. No. Okay. So let me combine codimension and ring in the sense that I'm going to talk about codimension 1 for a second. So codimension 1, almost nothing is known except we have a paper that was I'm so sorry, I wrote this wrong. I'm confused. This was not with Sander. This was with Dan Yasaki. My apologies. Jan Yasaki is the only one that was able of us to compute these groups in rank 2. That's so that was a very crucial input to all of this. And sorry, now is the paper by Coopers, Miller, myself, and Wilson. And that is that we have codimension 1 cohomology of SLN, let's say R vanish for n greater or equal to 3 if R is either the Gaussian integers or the Eisenstein integers. So that is 1 plus square root 3i over 2. Yeah, so this proof goes very similar to the proof of Church and Putman for Z, but it is to an extent more technical because you actually the geometry of Z or Z I Z the root of third root of unity, the geometry of those spaces, those lattices come in there. And I mean, we really prove that here that actually an analog of the Bukowski presentation is correct for the corresponding Steinberg modules. We actually find some other Euclidean domains where the Bukowski presentation cannot be correct. Yeah, so you basically, in some sense, if you think about Voronoi complexes in n equals 2, the only Voronoi cell that you have for Z is a triangle and is given by basically something, one vector, a linearly independent vector, and then the sum of those vectors. That's kind of those cells that you had in BA. And Bukowski literally says, oh, this is the Voronoi, these are the Voronoi cells for these rings, at least in a certain dimension. And larger rings have more complicated cells coming up. And that is really the problem here. So you would have to fix that somehow. Okay, and then for larger codimension, you don't have anything of this kind for other number rings. So this is the discussion, the whole discussion that we know of in the general pattern, what is known about the Church-Farb Putman conjecture type question for other numbers. So the next direction we could take is we can take subgroups of SLNZ, in particular congruent subgroups maybe. But so far, the only thing that we have worked on, and by extension, as we know, at least anybody has worked on in this matter, is congruence, prime level congruence subgroups. This is the only stuff that has. So recall gamma NP is a prime level. This is inside of SL and Z prime level congruence subgroup. And I mean, so I told you that Lee Sharba proved HVCD of gamma N3 is isomorphic to the Steinberg module of F3. Then I told you that together with Jeremy and Andy, we proved that this is isomorphic to an oriented version of the Steinberg module, or in other words, this homology group. But other than those two things, nothing is computed completely. There are some lower bounds. I think the best lower bounds currently are in a paper of Schremer. So best lower bounds for P at least 7. Now you can clearly see these things are not zero. Yeah, so don't expect these things to be zero. There's no Farb-Putman conjecture there. But how should I say this? We talked very, very shortly about homological stability in this conference, which means that at a fixed degree, certain homology groups stay the same if you go from SLN-Z to SLN+1Z. If you fix the ith homology group, then you get homological stability. And you should think of these this Church Farb-Putman conjecture as a homological stability result with Steinberg coefficients. I mean, there's always zero in the stability, which makes them isomorphic or equal. But even the other way around, if you could prove that they're isomorphic, then you would prove automatically that they become zero. Because if you combine two stabilization maps from SLN to SLN+1 to SLN+2, that map actually with Steinberg coefficients, that map is actually automatically the zero map. It's in that sense, it's a homological stability result. Now, if you take the homology, so fixed degree homology of congruent subgroups, it turns out you don't have homological stability. Yeah, the problem here is you have an action of SLNFP on these homology groups, and these are non-trivial actions. So you can't really have homological stability. You have always some representations that are non-trivial, and that has to grow in dimension. But you got something called representation stability. What is representation stability? Maybe you should view this. I'm not going to explain what all of that is in 2 minutes, but you should think of it as you have a certain representation. Let's say for the symmetric group, for every symmetric group you have the standard representation or the permutation representation, and those grow in dimension, but they're always kind of the same representation. For SLNZ, you always have the adjoint representation or the defining representation by acting on Q to the n. And so in that sense, you can prove that you can write each HI of gamma and P as in a fixed form as a representation. It grows in dimension, but it's always the same representation, if you will. And now here, we kind of observe the same thing, right? It's always the same representation, the Steinberg module. And so one might conjecture, and Church, Farb, Putman actually did this in a very loose way. They say, oh, there should be some kind of stability pattern happening here too for these congruent subgroups. And together with Jeremy Miller and Rohit Nagpal, we actually made this a little bit more precise and proved the following 2 results. So this is with Jeremy Miller and Rohit Nagpal. We proved that if you take the map from HVCD of any prime level congruent subgroup, and you can embed this, you can find a map into gamma n plus 1p. Now, this map is not an isomorphism. This map is certainly not a surjection, but I can view this, as I said, as a as an SLNFP representation, and I can take this SLNFP representation, induce it up to SLN plus 1FP, and get this map over here, and this is always surjective. And maybe there's a little bit more. This should be seen as a form of representation stability. So this means, in other words, if you take this, the image of this homology group in this homology group, and then span the whole thing as an SLN plus 1 FP representation, then it actually spans everything. And we have a similar result for codimension 1, but we were only able to prove this for prime 3. Namely, so this same statement, and the reason for that was that we were that in codimension 0 we have here the Steinberg module, and we understand the Steinberg module quite well. This paper was before the Miller-Putman paper, so we didn't have this yet. I'll mention this later. I think this would be definitely, this is a 3, and this is a 3, and this is a 3. It would definitely be worth pursuing for p equals 5. And I guess p equals 2 works the same way as this paper. It's that would not really be a new result. Okay, questions? All right. Now the last dimension is algebraic groups. Algebraic groups. So there's plenty of different algebraic groups that you can ask what happens in the VCD or below. And so far, there's only one that has been tackled as far as I can tell, as far as I know, and that is the symplectic group. And so a result of Paul Gunnell's basically says, and he told me that he wasn't aware that this says this, but this is quite immediately from his result, says that that in the top dimension, the symplectic group cohomology vanishes for n greater or equal to 1. And work in progress, and I'm a little hesitant. We hope to get this out this summer, but it's a very technical paper. So let me emphasize this is work in progress. By Benjamin Brück, myself, and Robin Sroka, is that we are proving this for codimension 1. Now, for some reason, which is not completely clear to me why that is the case, but for some reason, we need simplicial complexes for the codimension 1 case here that are analogous to the codimension 2 complexes for SLC. I don't know why, but we need that. So that's why this becomes so much more complicated. Okay, so this is the overview of the things that are known. Yeah, that's it. For these high dimensional cohomology groups in general, for these arithmetic groups, that's as far as I know, that's it. Now, I mean, open problem, solve every other case. I mean, that would be ideal. But as you could see, a lot of these are not really uniform, right? I mean, some of them are 0, some of them are something growing with Steinberg, some of them are growing with a class number, some of them don't have a class number and there come just random numbers 1, 2, and 6 in. So where does all of this come from? I don't think there is a chance of unifying this entire theory and just like proving it. There's no conjecture even, right, to unify this entirely. But let me tell you, maybe I have here 4 open problems that are hard. Yeah, I'm not encouraging a grad student to try to prove these open problems. But they should be, I think it's helpful to have a goal in mind, to have like a direction of where you want to go. And I think these are the next big milestones in this theory. So let me start with these open problems. Milestones. So the first one is simply the Church-Farb-Putman conjecture. Yeah, I mentioned this already multiple times now. I don't have to reiterate. Proving that for all, and I mean proving it for some codimensions larger, it would be great. But proving that for all codimensions, that I think that would be a great milestone. I would certainly, if I prove this at any point in my life, I will definitely send this to the annals if this is going to be proven. Yeah. So this is definitely a milestone. From what we've just seen here, I would very much also conjecture this statement for symplectic groups, or SP, Q, and Z. Honestly, so if you ask me, I would think this is maybe even true for Euclidean domains. That's if you ask me. That I think that that should be the goal, to prove this for Euclidean domains, and maybe this as well. Yeah, it's completely speculative. I mean, I have no, other than what I've shown you here, I have no extra data on this. Yeah, but it seems that is what I would try to do, and what I am trying to do. So these are both certainly absolutely. I would certainly recommend these for the annals, or if I be asked, this is what I think about that. Then so maybe also two open problems that are milestones, and I don't think are that easy. I don't know if, depending on how the proof goes, what comes out of it, I don't know if they're quite annals worthy, but still very, very hard and good, would be to figure out, calculate what is actually the group of top cohomology of these SLN of numberings, in particular if OK is not a PID. I imagine you might have to do that for rings individually. I think probably you will not be able to prove this for all number rings, what this is, or figure this out. I could imagine that you will have to start with the smallest non-PID that you can find with class number 2, and try to prove maybe something something about that. So in order to have any kind of idea what's going on there, I recommend then reading the paper of Church, Farb, and Putman there first. And then I also think that calculating what happens in the VCD of gamma and P, yeah, that you can do with integral coefficients, because there's no torsion in these for P greater than 3. So in particular for P is greater or equal to 7. I think this is going to be, if you can do this for all P, I think this is a very, very strong paper as well. Again, this might be hard. Yeah, I mean, you have this result, which should tell us everything you need to know about this happens in, oh, maybe I should say this here. This is for n greater or equal 2, and this is for n greater or equal, I forgot. Some number. Let me lie. I might be 4 or something. I'll look that up later. But you have this result. So this tells you that in some sense, everything you need to know about this group happens in rank n equals 2. So, but in another sense, it doesn't. So there is some kind of cuspidal cohomology in rank 3 for some primes. For 7, there is cuspidal cohomology in rank 2. There's none in higher ranks. For 11, I believe Schwärmer told me that there is also cuspidal cohomology in degree 3. But then it is known that there's no higher cuspidal cohomology. in codimension 0. I don't know what you think about this. This seems hard in general. Okay, so these are the milestones. And so maybe now I want to go to some more achievable problems. And so some of these, I might even have ideas already what you do. If you want to work on these, it's certainly useful to send me an email. I can provide you with some ideas where to start. Or I can also tell you if I, in the meanwhile, figured it out myself, gave this problem to a grad student, another grad student, or if somebody else is working on it. Yeah, you don't want to, as a grad student, it's not going to be helpful to work against somebody at the same problem. Right? If you can work with somebody at the same problem, that's going to be nice, but that has to be facilitated somehow. You have to meet that person. I think playing with open cards there is probably a good idea. I understand that it's always hard as a grad student when you only have so many ideas. But let me tell you something here. Let me start with the following. I'll define a simplicial complex. So BP, let's say BPNR let's say for R a PID is supposed to be a simplicial complex. And so what's the vertices? So vertices are one-dimensional summons of R to the N and two-dimensional summons of R to the N. That's the vertices. And then it's a simplicial complex. So it's enough to tell you what the top simplices are, and then every other simplex is just a subset of one of these top simplices. So top simplices are given by one plane, so one two-dimensional summand, and n lines, such that so this is a plane, these are lines, such that L1 ... O plus Ln is equal to Rn. And after reordering, maybe L1 plus L2 is equal to P. This is a simplicial complex, and you should think of this complex of, in some sense, generalizing BA. So if you recall, let's say for Z, the complex B B2 is just a fairy graph in I'm sure I might still have that here somewhere. It's just a fairy graph in the Poincaré. Oh, here this is. And then in BA, we filled in all the triangles. Now in BP, what we do instead of filling in all the triangles, we take one point and cone everything off. So we just get a cone with all of these things. So that would also be contractible and would be, I mean, it's just another model for the same thing. But it would also work if in your Voronoi 2 picture, if for other rings, you don't have only triangles. You'll have other kind of Voronoi cells here. So that's kind of the idea there. So what's the problem? So one problem is show that if R is a Euclidean domain, that BPNR is as highly connected as BA. So that would be show that this is n-1 connected. Why would that help? This would show that the codimension 1 cohomology of this would show that the one homology of SLNR with Steinberg coefficients is 0, let's say, for n at least let's say 5. Maybe smaller, but at least 5, let's say. And so in particular for number rings, if R is a number ring, then this would also then apply BCD codimension 1 of SLNR Q coefficients is 0 in that range. So that would generalize the theorem by Church-Farb and that to all Euclidean domains. Yeah. If you could prove that let's say, so for R equals to OK with K equals to Q square root of D and D equals to -19, -40. What did I write? -43, -67, -163. If you can prove here that BPN R is at least as connected as partial basis complex, so this much connected. Now the partial basis complex is not connected, not n-2 connected in this case. This is the problem why you don't have. This is the problem why you don't have 0 here. I guess you do have 0 here, but you don't get 0 there. But if you could prove it for this, then this would indeed imply that actually that the BCD of this SLN, okay, sorry, with Q coefficients, is equal. These are actually equal. So equal to 0 Q to the 2n Q to the 6n if D is equal to -19, D is equal to D is equal to 1 -1, 63. So that would give you that these are actually equal signs. And again, this is only for the even ones, so one has to think a little bit more what to do there for the odd ones. Okay. Now, let's see. Now, when it comes to HVCD of congruent subgroups, there's lots of things you can think about. So let's say this is a congruent subgroup in SLNC or SP2NZ or SLNZI or SLNZ, let me use omega. There's lots of things to think about here. In particular, in all cases, you should think about what happens for n equals 2. Yeah, can you prove something for n equals 2? Can you prove, there's always this map to h n minus 2 of the corresponding Tietz building. I guess for the symplectic it's n minus 1, but let me just write it like this. Mod gamma, or I mean, sorry. Yeah, let me just write it like this. So for these you have not of q but of qi and q omega. So what happens for n equals 2? Is that equal to this? Is there any cuspal cohomology that gets in the way for this? And once you have one of the things where you know the prime is low enough that you don't have cuspal cohomology, then this is worth asking, is this equal in general? What does this even mean? You can think of different sequences of congruent subgroups. You can think of principal congruent subgroups for these other groups. You can think of non-principal congruent subgroups, gamma is naught or gamma 1, and make a sequence out of those. Those embed into each other. You can think about those, and especially the gamma naughts should be considerably smaller, so they should be very amenable to computations, to actual computations for low n, much better than the congruent subgroups that I was complaining earlier to Philippe about. And then I want to mention, I already did mention this, that's a nice thing about writing. You don't erase anything. You can always show it again. As I said here, we only were able to do this for for p equals 3 because at the time we only knew what it was for what the codimension 0 was for p equals 3. But I think that I believe I have a good idea of some methods that you could use to show something similar for p equals 5. Oh, I forgot the -1 here. -1. Gamma n plus 1. Yeah, so now that we know what this is, I believe that we can use actually some similar methods there. I mean, again, if you actually want to work on that, I feel free to contact me. I would provide you with some more information about this. And then maybe as a final, and maybe I should leave this open, maybe as a final problem that's also definite, that should be very manageable, not easy, but manageable, is what happens to these hacker actions on HVCD of gamma and p for p small equal to 5. I mean, maybe Philippe knows, but I don't know if this is just explicitly calculated how these hacker operators act on the top cohomology of gamma n3 in general. I mean, it's computed, so one should be able. This should be. I mean, they should all be Eisenstein actions, and so this means it's relatively easy. But what it is concretely, I don't think it's known. I think it'd be worth computing, and it's certainly I'm certainly not known for 5 because we only found what it is a couple of years ago. So that is definitely something. So this here you would come in what Paul was saying, that you can use some modular symbols, which is the same thing as apartments, and you should be able to apply your Hacker operator on it, and then you have to whatever comes out bring back into the form of modular symbols, into integral modular symbols, integral apartments. I think that's something that can be done. It means you have to understand things really well. You have to understand how this isomorphism goes really well. You have to understand how these Hacker operations go really well. You have to understand how to make integral apartments, turn them back, rational apartments, turn them back into integral apartments. So you would learn a lot of things on the way. Even if you don't solve this completely, it'd still be helpful in that way. And I believe that is all I have to say, which is perfect with the time. So I thank you for your attention. Any questions? Yeah.
I have a question. It might be nonsense, but for these principal ideal domains that are not Euclidean, are there like some local global principles available, or is this?
I can't even tell you whether that question is nonsense or not. So wait, where was this? Here. Can you elaborate on what you mean?
Yeah, like you're working with like rings of integers of number fields. So what happens if you consider the local case and work over the rings ZP, for example, or like some extensions of them? And maybe that's easier, maybe not, because I don't know how the homology for them looks like, and I also don't know if you can deduce from the local homology something about the global one.
I see. So like a ZP kind of version of p-adic version of
you consider all completions, and maybe that's.
I think this is actually a great addition to the problems. Is question what happens for HI of SL and ZP, yeah, and then with coefficients in Steinberg of, I don't even know of what, probably something like QP or something. I don't know. What is this? I think that's a great question, and yeah, maybe there's some local principle. We haven't gone into that at all before, yeah.
Because you pretty much know some stuff about integers, so maybe if you can figure out those for the local cases,
yeah,
just for the base rings ZP, so maybe you can see some connection or something like that.
Yeah,
maybe there's something there.
Yeah. I mean, as I said here in the beginning, for fields we know it, for any field.
Yeah.
So this kind of, but so if you can reduce it to the residue fields of these things, then you're definitely in business because you have that result. But the question is the reduction. That's I don't really see how that would work, but worth thinking about.
Yeah, something.
Oh, please.
So in fact, in the Borel model, in the Hermitian case, even if there are computations which have been performed in the PATZT case, but most of the machinery works for non-PATZT. So in fact, so in particular, if you are interested in the top cohomological dimension, so it means the lower dimension of the Borel model, then it could be possible to do something.
Do what?
Well, to perform computations without the PID assumption. That's what I mean.
Mm-hmm. No, I mean, Voronoi doesn't have any limitations on being PID. That's or as far as I understand. It's just getting more computation, like just longer.
Yes, but you have the perfect form classification. I mean, you need to have several layers of stuff. You're right. I mean, you do not necessarily require PID, but for some computation at some point, it could help. So if it is not PID, it is more complicated. But, just what I mean that maybe it's there could be a way to attack this problem on this angle.
No, for sure, you can do something computational there, and try to figure out. I mean, even just I said we want to find out what this is. Even finding this concretely for n equals 2 would already help say something, like would help understand, oh, is or like whatever for n equals 2 or 3. For n equals 2, this just says it's greater or equal to the class number minus 1. Is this everything? That's worth looking at. Yeah. So those are interesting questions for sure. So so mainly the goal is to say there is so much to do and not many people necessarily doing things on it, and still it's like interesting to people. I'm not saying it's easy, but yeah. So that's my advertisement for the field, basically. All right.
Any other questions? Questions on Zoom? So disclose. So thanks the speaker again and disclose the second week. So see you next week.